Hello and welcome to part 3 of time constants, this time looking at the very important derivation of the discharge of a capacitor through a resistor. This is the problem that we're trying to solve. What happens when the switch is closed and the charge on this capacitor is allowed to flow out through this resistor? Well, you can see that just after the switch is closed, there will be a voltage across this resistor. Therefore, there will be current flowing around this network as some of the charge on the high voltage side of the capacitor moves around the circuit and fills up the low voltage side of the capacitor. You could think of that elastic membrane in the barrel just moving back to its center rest equilibrium position. After it's done that, after an infinite amount of time, there will be no pressure difference across the barrel, i.e. no voltage across the capacitor, which means no voltage across the resistor, no current is flowing, and everything is stable. So we know what happens just after the switch is closed, and after an infinite time. What we're trying to work out is what exactly happens in between those two times. And to do that, we need to do a bit of maths. So let's define some terms. We'll have a capacitor here, which starts off with a voltage across it of value V0. The voltage across the capacitor at time t equals 0. And that is going to be connected through a resistor down to its other side. And to make my life easier, I will define this point in the circuit as my local reference of 0 volts. So the voltage at this point here is just equal to the voltage across the capacitor. At time t equals 0, that's just equal to V0. In general, it will be at a value of V, which will be at a function of time. The value of the resistor is constant. But there will be a current flowing down through the resistor, given by Ohm's law. The voltage across the resistor is just V, a function of time. So the current through the resistor, I'll call that I, function of time, is just the voltage across the resistor divided by the value of the resistance. That's the current flowing down here. We also know that the current flowing onto a capacitor, I, is equal to C times D, delta V, dt, where delta V is the voltage across the capacitor. Well, once again, that's just going to be V, a function of time here. I can write it like that. But bear in mind, this is the current flowing onto the capacitor. The current flowing through the resistor must be current flowing off the capacitor in this direction, the other way, because it's the same current flowing off the capacitor that's flowing through the resistor. So the current in the circuit here, the same current that I've put into this equation, I of t, is actually minus the current that's flowing onto the capacitor, minus C delta V dt. Or, if you like, you could define the current flowing through the resistor as being IR, the current flowing onto the capacitor as being IC, and apply Kirchhoff's current law and get that IR plus IC must be equal to 0, and therefore IR is minus IC. That works too. As long as you get to this final expression here, and this expression here, that's fine. Because we can then equate these two currents and end up with V, as a function, which is a function of time, divided by R, is minus C dV dt. It's a differential equation. If we want to solve this to work out what the voltage actually is as a function of time, we need to integrate it. So, collect terms on this side, we'll get minus dt over CR, and on this side, dV dt by, dVt over V of t. bringing that down here and that up there. And now we're ready to integrate. Limits of integration. Well, the time starts at 0 and moves on to some particular time, t. The voltage across the capacitor starts at V0 and heads on to a value V some time later. Integrate these, we get minus t over CR equals, and dVt over v of t, in fact dx over x, is the natural logarithm of x. Oops. And we can apply that result here and get that this is natural logarithm of the voltage, and the limits are v and v0. So this is equal to the log of v minus the log of v0. And we can use that useful result from logarithms, that the log of x minus the log of y equals the log of x over y, and write this as the log of v over v0 is minus t over CR. Taking antilogs of both sides and multiplying up by v0 gives us the final result. The voltage, this voltage here, which is still a function of time, is equal to v0, which isn't a function of time, it's just the voltage the capacitor had at the beginning, times e to the power of minus t over RC. And that is our final result. If you plot it, it looks like this. It's a characteristic smooth curve known as an exponential decay. And one useful figure to remember is that after one time constant, now a time constant is defined as the time after which you're taking v0 times e to the power of minus 1. So the time constant in this case would be r times c. And we can write this formula in terms of the time constant as v, the voltage of time, equals v0 times e to the power of minus t over tc, the time constant. When t is equal to the time constant, then we get the voltage is equal to v0 times e to the power of minus 1. E to the power of minus 1 is 0.368, so we're at 36.8% of where we started after one time constant. The time constant in this case is just the product of the resistance and the capacitance. This is a general formula for exponential decays. Initial value, I'll call that IV, times e to the power of minus t over the time constant. Here, our initial value is v0, our time constant is RC. Okay, that's enough about discharging capacitors. Next time we'll have a look at charging them up in the first place.